Welcome back to Unit 2 of our course, and this is Lecture 5. Now, if you remember, what we did in Lecture 4 is we took this function n of p from Lecture 3, which came from this idea of counting states using the periodic boundary conditions. So that's this n of p, and what we did was combined it with the energy momentum relation to get a density of states. And what we want to do in this lecture is kind of do the same, but now we want the number of modes, which is a slightly different quantity. And if you remember, the way it's defined is this number of modes is related to the ballistic conductance, which depends on density of states times the average velocity. And this average velocity involves a numerical factor that usually depends on this number of dimensions that we're involved in. So this is in 1D, that average, you just have this 1 here, 2 over pi, and this half. So this number of modes then is given by this expression with 3 different constants depending on 1D, 2D, or 3D. Okay. Now, we already have an expression for the density of states. So in principle, all we need to do is multiply it by the expression for velocity, and we would be done. And we would have an expression for m of e. See? But instead, I'm going to do this in a slightly different way, because it also introduces a very useful relation that I wanted to introduce. And that relation is a very general relation, independent of what energy momentum relation we have. You could have any relation here, doesn't matter. Density of states times velocity times momentum is equal to n. N is that quantity. As you know, these functions, they are functions of momentum, or you could view them as functions of energy if there is a given energy momentum relation. So density of states times velocity times momentum is equal to this n times the number of dimensions. So let me show you where this comes from, because this is a very useful relation, independent of the specific energy momentum relation. And we'll use this then to obtain an expression for this number of modes. Okay. Now, what we do is we start from this rule that we discussed in Lecture 3 using the periodic boundary conditions. And remember, this doesn't involve any energy momentum relations. It just is based on this idea of discretizing momentum using the requirement that the number of wavelengths fits into your box. Now we take that quantity and take its derivative. So dn dp. So when I take the derivative, what do we get? Well, these are all constants. They just stay whatever they were. 1D, 2D, and 3D. Makes no difference. But because this is p over h to the power d, the h to the power d stays as is, but the p to the power d gives you d times p to the power d minus 1. That's just this rule of differentiation. P to the power d, we are differentiating with respect to p. Now the next point to note is dn dp you could write as dn de times de dp. And we could multiply both sides with p. Now let's look at what we have on the left-hand side. We have p, we have dn de, which is density of states, and then we have de dp, which is the velocity. So on the left-hand side, we have density of states, velocity, and p. What do we have on the right? Well, we have the number of dimensions d. And then if you notice, whatever we have here, once we multiply by p, this p to the power d minus 1 times p becomes p to the power d. And so we basically get back what we started from, namely the n. And so it's just d times n. So this is the basic relation that I was talking about. It's independent of energy momentum relation. We have made no use of the specific relation at all. We have said de dp is velocity, but we didn't assume any particular form for it. Okay. So now let's move on to what we want to do, namely use this relation to obtain an expression for the number of modes. Now, the expression we had before is what I've stated here. Modes is proportional to density of states times velocity. Now, instead of dv, I can write nd divided by p. So I could do the following. I have this h over 2l right where it is, and then dv becomes n times d over p. Next, what I do is, for n, I use this original expression from here. So you see, we had this p over h to the power d, and here I have an h over p. So when I multiply it, it becomes p over h to the power d minus 1. The two l's right there. We have p over h to the power d minus 1. And then I have this constants in here, the 1d, 2d, and 3d constants. How do I get that? Well, I took the 1 from here, multiplied it by 2l, because n has this 2l in it. So 1 times 2l gives me 2l. Next, I have this 2 over pi and pi wl. So when I multiply, I get 2wl. Well, why do I have 4 here? Well, that's because it's also multiplied by the number of dimensions here. So here, this is 2 dimensions. So it's 4wl. And similarly, half times that is 2 pi over 3al. But then it has to be multiplied by the number of dimensions, and so you get 2 pi al. So finally, you see, you have this expression for m, and you can divide out the 2l all the way to get an expression for m. And you'll notice how similar this expression is compared to the expression for n. And I'll have more to say about this. N has this p over h to the power d. M is p over h to the power d minus 1. Okay? Here you have 2l, here you have 2w. So it is as if with modes, one dimension is just 1 here. I mean, in one dimension, d is 1, so this is 1. So basically, number of modes is 1. But 2 dimensions, it's kind of like the one-dimensional result from here. Instead of 2l, it's 2w. And for 3 dimensions, the cross-section is, of course, 2-dimensional. And so you kind of have the 2-dimensional result from here, pi a. So you notice this similarity. Whatever is in 1D here kind of appears in 2D. Whatever was 2D here appears in 3D, and so on. So we'll talk more about that. So what we have done then is, we took this expression from lecture 3, then this general identity that we talked about, and took this expression for modes from unit 1, and used that identity to get an expression for modes that looks a lot like the expression for n. And so far we have just done some algebra, you see. But this is kind of important because it gives you a totally different physical interpretation of what m represents, you see. And for this purpose, what I'm going to do is take this expression and just rewrite it in a slightly different way. You see, if d equals 1, then as I said, that amounts to 1. If d equals 2, then this is like p over h times 2w, which you could write as w divided by h over 2p. And similarly, the last one you could write as a divided by h over 2p squared, and then a constant in front. Now, what do we gain by doing that? Well, remember, h over p is what we call the de Broglie wavelength. So what this quantity tells you is how many half de Broglie wavelengths fit into the width of the conductor. That is, if you have a two-dimensional conductor, length L, width W, then the number of modes is basically how many half wavelengths fit into that width. Right? Now, if you had a three-dimensional conductor, so then the cross-sectional area is A, then this tells you like how many half wavelengths fits in this way and how many half wavelengths fits in that way. And it's a product of the two. That's what it is. Area divided by half wavelength squared. So this is this idea, those of you who are familiar with electromagnetic waveguides will also recognize that that's kind of what determines the number of transverse modes in an electromagnetic waveguide. I mean, that's where the word modes comes from. But the point I wanted to make is this very important distinction, this of these two ways of looking at what number of modes means. The one view is the view we had from unit 1. That is, it's like density of states times velocity. Density of states tells you how many states you have, velocity tells you how fast they move, and so the product kind of determines how much current you can get. So that's why modes depends on density of states times velocity. But a totally different way of thinking of modes is you look at the cross section, see how many half wavelengths fits into it. And this is the view that most people who have some familiarity with this would have heard of. This one is less widely appreciated. And what I was trying to show is if you make use of that identity, then you can transform this into this, which represents two totally different physical views of what number of modes means. And incidentally, I should point out that just as the way I've taken M and written it as number of half wavelengths that fits into the cross section, you could similarly take this function N and write it in a form that looks like how many half wavelengths fits into the volume. That is, if you had a one-dimensional solid, it's like the length divided by half wavelengths. Otherwise, it's the area divided by half wavelength square, or the volume divided by half wavelength cubed. So N kind of tells you how many half wavelengths fit into the entire volume of the solid, whereas M tells you how many half wavelengths fit into the cross-sectional area of the solid. Now, one important consequence of this is this ballistic resistance that we talked about in Unit 1. That is, I'd mentioned at that time that if you just look at this expression, it would tell you that the number of modes is proportional to the width or the cross-sectional area. What that would mean is you'd expect that the ballistic conductance would change linearly with width or cross-sectional area. And this is observed. This was observed back around 1970 or so, and sometimes people call it the Charvin resistance. But the very important development that came some 20 years later was that in devices with small cross-section, where the number of modes was relatively small, not thousands, but more like tens and twenties, that's where people saw this very nice quantization of the ballistic conductance. That rather than go linearly, it actually went in steps. Now, how do you understand this? Well, the idea is that actually M is not quite that quantity, but rather the integer part of that. In other words, if this happens to be 2.5, then it's actually really 2, because the number of modes is given by, again, how many states are available in that cross-section, which can only be 2 or 3 or 4. It cannot quite be 2.5. So the correct expression is, it's the integer part of this. Normally, you don't worry about it because if it's a big number, like 10,030, then it really doesn't matter if it's 10,031. And in any case, of course, if these steps are very close together, you see, in other words, you always have to average over energy. Because one point I've mentioned before, although we're not writing it explicitly, is that whatever we get as a function of energy has to be averaged with this dF/dE factor. That is averaged over an energy of kT. And that tends to, I guess, smooth things out when you're at higher temperatures. But at low temperatures especially, with conductors with small cross-section, this is now a very well-established phenomenon. It was first seen in semiconductors, like I believe it was gallium arsenide. Since then, people have seen it in all kinds of materials, including even a small hydrogen molecule. Okay? And this idea that why it is quantized, you can understand by this view that M is actually the integer value, integer part of that quantity. Okay. So that kind of completes what we are trying to do here, namely introduce this energy momentum relation, then introduce the rule for counting states, and use that to get density of states and density of number of modes. Next, in the next two lectures, what we want to do is talk a little bit about the electron density and try to relate our conductivity to the electron density. That's what we'll be doing next. Thank you.